let's see, 15th place. Looks like Selena got 15. All right. There we go. We're gonna switch to our. We have two new formulas today. These are both very easy, and then we got a couple real world problems we're gonna look at with them. You don't have to log into here if you don't want to. I don't have any questions for to answer, but if you want to see it on your screen, you can log in there. Or it's up to you. But if you log in, the notes won't take very long. But there's a couple more things we're going to learn in this section. Two formulas, again, that are very easy, and the assignment will be pretty quick. The 6.1 is a lot of pretty easy stuff, just a lot of different things, but it's all pretty easy too. So I would just make sure you write down the two formulas, you'll need those, but other than that. So the two things we're going to learn are called arc length and sector area. They both have to do with angles and also circles as well. Arc length and sector area. So first up is arc length. So anybody know what an arc is?
I think every should travel with an arc.
Okay, yeah, so kind of the path that you can travel for you to say. You can think of it as the unit of kilometers. Okay, yeah, like a line between two rays. Yeah, exactly. That's good. Yeah. So kind of a curved line, right? You can think of like a curved line. Someone in second period thought I was referring to Noah's Ark, which is similar, but Noah's Ark is spelled with a K. So, but if you think of the boat, I guess like Noah's Ark, it kind of has that shape as well. There you go. If that helps you think of like Noah's Ark. But yeah, an arc is actually arc with a C in math. Is basically a distance around the outside of the circle. So if we have an angle like this, it's the distance traveled from here to here. This is called an arc. There, C's arc. So if we're looking for an arc length, we're basically thinking if you were to sort of travel along this curved path, how long would you travel? How far would that be? So that is what an arc is. So then an arc length, it's just the distance along this curved line, which we call arc, on the outside of the circle. Basically, if you're going to travel around the outside of the circle, how far would you be traveling? That would be the arc length. This has a couple important parts. Obviously, I have the arc out here. These are both radii of the circle. Both of these is the radius. It's the distance from the center to the outside edge, right? And then we have an angle in here, and this angle we're going to call the central angle. The central angle. Arc, central angle, and a radius. Central angle is just an angle formed by two of the radius, and it's at the center of the circle. So the formula for arc length looks like this. S equals theta over 360 times 2 pi r. It might seem like there's a lot of different symbols to memorize, but I'll show you where this comes from. Theta over 360, theta is the central angle. S, what do you think S represents? Yeah? What? It's just the arc length, actually. S is just the letter we use for arc length. S is arc length. S, arc length. Theta, as we said here, this is a theta. That's just the symbol we use for angle. So theta is the symbol we're going to use for a central angle. And then obviously 2 and pi are just 2 and pi. And then r would be a radius. So the arc length is theta over 360, so central angle over 360 times 2 pi r. Let's think about where this comes from. What is 2 pi r? What is that? Close. If it's 2r would be the diameter. Yeah, Anya? Yeah, what formula is that? Close. Yeah, this is circumference, yeah. You're close on the area there. So this is actually just the circumference of a circle. So circumference, if you remember, that's the distance all the way around the circle, circumference, right? So this would make sense. We're sort of just taking whatever fraction of it, okay? This is the number of degrees over 360, so this is just a fraction of the circle times all the way around the circle. So if it was 90 degrees, that's like a fourth of the circle, right? So it'd be a fourth of whatever would be the circle. So this is just the circumference, you can just remember that, times basically the fraction, okay? Fraction of the degrees. So fraction degrees over 360, however much we have over 360, times the circumference. That's it. Very easy to use. All you're going to do is just plug it in there. And I have a real world problem we're going to look at here to solve.
Okay, so our second example takes us out to a track and field event. Jordan and Tyler are teammates and partners on a relay race, and they're running on a curved track with a radius of 25 meters. We also know that Jordan's location is 153 degrees away from Tyler's. Now what we want to find is the distance on the track between the two runners. So let's go ahead and visualize that curved racetrack. And since Tyler and Jordan are in a relay race, they're spread apart. They're on different locations on the track, and they have to meet each other and pass off a baton. So let's call Jordan's location J and Tyler's location T. Now we already know that the radius of the curved portion of the track is 25 meters long. We also know that Jordan's location on the track is 153 degrees away from Tyler's. Now it's important to visualize that Jordan's going to have to run on a curved path along the track until he reaches Tyler and hands off the relay to him. So,
all right, just take a second and see if you can calculate that arc length there. Well, this portion of the track is. Okay. It's not overall, but this is like a half circle. So this is a circle. If you went past like the here, it wouldn't work. It's not a circle. But all tracks are curved on this. So this is like a half circle. Because if you cut out the middle part, chop it and squeeze it together, you would get it.
Either way, it's still really equal. Like he starts at the beginning of it, and he starts at halfway through it. Like probably very do that.
Yeah, I don't know exactly where the starting spots are. Or, I guess that would be like a 4x1. Is everybody around 4x1? Did you ever run track? Okay. I think it's actually pretty close to what it actually is.
Really?
Well, because it's divided into fourths, so if you think about
So
it seems like
probably,
four.
yeah, probably the whole curve. And then probably the straight line.
So if you didn't write down the formula, S equals theta over 360. And then, so I would put that in parentheses, and then 2 pi r. So when you plug this in, I would do it like this. Parentheses, our theta is 153 divided by 360. And then I would probably do a little time symbol, 2 pi, and then substitute in an r, which is 25. And answer. So we get the right answer. 66.8. Oops, I did not mean to click on that. All right, so we're gonna look at our next one, and then we'll come back to the other. So our next formula is called sector area. Sector area. Got a little picture to represent this. Another circle. So we got a circle. Let's draw a similar deal here. We got the same thing happening. Area obviously is a little different than length, right? Area is two-dimensional. So a sector area is basically area of this little wedge that we cut out. You can think of it as like a slice of pizza. Cut out a slice of pizza. Really, I think pizzas, they should actually call them sectors of pizza, as in slice of pizza.
It's kind of weird though. That wouldn't be funny if you were a nerd though. Like, if you're like, hey, brother, pizza here, can I get a sector of it? Like, they look at you like you're an idiot.
It at least works for round pizzas, right? Sector. A sector of pizza.
Why don't you pursue comedy?
Doesn't pay well enough, I guess.
Meme doesn't pay well enough. What?
That's funny to hear that. I've heard the teacher salary.
Not too bad. So yeah, you can refer to it as a sector. You can ask how many sectors does the pizza come with in the sector. Because someone in the other class thought sector pizza sounds like a cool pizza restaurant name. Sector pizza.
Yeah, it's like
Oh, yeah.
Hey baby or something like that. Like I like the sounds like Toy Story. I think the pizza planet would have something like that. Like have a sector pizza.
So that's what a sector is. So the area would be like you're taking a slice of pizza out. So theoretically, you could figure that out if you took out a protractor and cut out your piece of pizza. You measure the angle of the protractor, and then you measure how far it was across. You could find the diameter, and then you could find the area. So you could find the area.
When you go to the listen, so you have taken more than they need to, right?
Don't worry, I've never done that before. So a sector area is the area of this section formed by an arc, which we already talked about, and the central angle, which is this. That's sector area. And the formula is kind of like the last one, except instead of taking like theta over 360 times the circumference, what do you think that would be?
Pi r squared.
Yeah, pi r squared is the area. So theta over 360 times pi r squared. That's the area. So this is like the portion of the entire area. So it's a pretty intuitive formula. Obviously, A is the area. Theta is central angle. And R is the radius. It's again very easy to do. You just plug them in. We got a word problem for this one. It's not pizza, unfortunately. It is wiper blades. Which I had to use my wiper blades this morning. It's kind of frosty.
What's up, everybody, and welcome to this lesson on arc lengths and sector areas in the real world. So let's go ahead and jump right into our first example here.
Solve this
And we'll
one.
start off by highlighting the key information. We have a 14.75 inch long windshield wiper blade that is swiping up and down on an arc with an angle of 132 degrees. And what we want to find is how many square inches of the windshield surface is the blade covering on any given swipe. So first thing I do is I visualize the front windshield of a car, and actually in my mind I don't like this color, so let's go ahead and change it. That's better. Okay, so now that we're going to roll with the chrome pink colored car, we really only want to focus on just that front windshield. Let's go ahead and zoom in on that area. So as our blade moves on an arc, it's covering a portion of that windshield, and we want to know how many square inches is the area of that space that's being covered by the windshield as it swipes back and forth. Now we know the length of the wiper blade, our radius, is 14.75, and the measure of the central angle is 132 degrees.
All right, go ahead and give that a shot real quick. It's S equals theta over 360 times pi r squared.
And since we want to find the number of square inches that make up that contained area, we're going to use the sector area formula. Now for our formula, we need two things. We need the value of theta and the length of the radius, 2. R squared with 14.75 squared. And then I just have to evaluate the rest of the formula, which should leave us with a sector area of approximately 250.6 square inches, the surface area of that sector.
There you go. So this actually would apply maybe if you're in the auto programming. This maybe if you're designing wiper blades. So think about if you wanted the wiper blades to cover a certain percentage of area that we were going to cover 80% of the windshield. So then you would have to figure out the area of the windshield and figure out the area of the sector that you would need so that you can then find the length of that. There you go. Now it's turned off. So as far as problems, you do have a delta math for these problems, and I'll pull those up real quick. You had 8 of each of them. They shouldn't take you long, and you might actually finish them still before you leave. But just to show you the notation here that they use, just it looks a little bit different, but it gives you just a picture of a circle. It tells you the measure of an angle. So this is this central angle, 56 degrees. And it's going to give you just 2 letters, RS, that's just a radius. So it's always going to give you a radius in the central angle, so you're just going to plug them into the formula. So for arc length, it's S equals theta over 360 times 2 pi r. And then for area, it's theta over 360 times pi r squared. So it's going to be, first one, just using arc length, plug it in. Now it does want you to round to the nearest hundredth. That's the second decimal. So round to the second decimal means you'll look at the third one and then you round up or down to the nearest hundredth. Okay. So you got 12 minutes to get started on that. You may get it done before you leave.